Alright, welcome back to our physics review. This time, we're moving on from kinematics to forces. So in this video, we're just going to go over some basic concepts, and then later on, we'll get to some examples. Alright, so I just wanted to talk about what a force is and what inertia is. These are two important concepts that we'll go over later on, and you'll use throughout multiple physics problems. So let's start with a force. So a force is an interaction between two bodies. Cannot be a force without two objects. That's important to remember. And it's either like a push or a pull between two bodies. And a force results in an object speeding up, slowing down, aka a change in motion or an acceleration. So that's what a force is. And in the first example, we see a man pushing a box. So we have two bodies, and it's resulting in the box speeding up. And then here we have a pull. It also results in the box speeding up and changing direction. So that is what a force is. And now let's go on to inertia. Inertia is an object's resistance to a change in motion. It's not an object's resistance to motion, but resistance to a change in motion. It's important that you remember that distinction. So we have two examples once again, and this just demonstrates how inertia is related to the mass of an object. So this, we can say, is 10 kilograms, and this is 1 kilogram. So if this is the same guy, if he was to try to move each of these boxes, he would have a harder time moving the 10 kilogram box than the 1 kilogram box. And in this way, we see how inertia is related directly to mass. As mass increases, an object is more resistant to change its motion.
All right, so now we're going to cover Newton's laws, specifically his first three laws. So for the sake of explaining it, we'll start with Newton's second law. So Newton's second law states that the acceleration on an object is directly proportional to the net force acting on that object and inversely proportional to the mass of that object. And the direction of the acceleration is the same as the direction of the net force. So from this law, arguably the most important equation in all of physics is derived, which is that the net force equals the mass times the acceleration. Now force is commonly measured in newtons, and a newton is defined as a kilogram times meters times seconds to the -2, or a kilogram meter per second squared. So now we'll move on to Newton's first law. Newton's first law states that an object in a state of rest or motion will remain in that state unless acted on by a net external force. Now this is most commonly observed in space. If you send an object flying in space where there's no net external force acting on it, the object keeps moving in whatever motion it was originally put into forever until it is acted on by an outside force. However, it's also important to recognize that it is it's a net outside force. So if you have an object already in motion, let's say this box is sliding to the right, and you simultaneously push it with a force of 5 newtons to the right and pull it with a force of 5 newtons to the right, it will experience no acceleration. It'll just maintain its original motion. Now let's move on to Newton's third law. Newton's third law states that whatever force one object exerts on another, the second object exerts an equal and opposite force back on the first object. Now this is one law that's commonly misused or misseen. So an example that appears in physics a lot is if the Earth exerts a gravitational pull on you and you exert a gravitational pull on the Earth, which one is greater? And most people are inclined to say that the gravitational pull that the Earth exerts on you is greater. However, from Newton's third law, we know that these forces are in fact equal. However, if we take a look at the equation from Newton's second law, F net equals ma, we know that the mass plays a role in this. So these forces are equal, but what's really happening is that because the mass of the Earth is so many times greater than the mass of a single person, the acceleration that a person causes on the Earth is insignificantly small and immeasurably small, whereas the acceleration that the Earth causes on a person is very measurable and very apparent. And those are Newton's first three laws.
Okay, now we're going to do a forces practice problem using the 3 laws that we went over. Okay, so the problem is 69 Newton force is applied on block A, which sits next to block B on a frictionless surface. What is the acceleration of the two blocks, and what is the force that block A exerts on block B? So to figure out this problem, the best approach is to start with considering this entire system. So what we're going to do is we're going to try to find the acceleration of both blocks, and consider them as like one block. So we're going to combine the two masses. So what we want to write, the first step is to write our equation, since we already have a diagram of what's going on. So I'm going to write sigma F equals M, and it's the mass of both blocks, so I'll just call it M, A, B, and then times A. So now it said to find the acceleration of the two blocks, so it's a simple division, and so A is going to equal sigma F over M, A, B. So now we have an expression for the acceleration, and we can solve for that easily. So what we can do is plug in our values of 69 Newton force, 69 over mass AB. So we have A and B, so it's going to be 20 plus 10. So the acceleration of the system is equal to, let's see, 69 over 30 is 2.3 meters per second squared. So we answered the first part of the problem. Now we have to deal with the second part. What is the force that block A exerts on block B? Now, be careful here. It is not 69 newtons. It would be different. So we're looking at forces exerted on block B. So what we're going to do is take block B into consideration only. So we're going to be using the mass of block B with the acceleration that we just found to determine a new force. It's not the net force. It's simply an internal force acting on block B. So we have to rewrite this equation, but for the force of A exerts on B. So A on B is going to be equivalent to the mass of block B, mass B, times this acceleration A that we already determined. So then we just plug in the values and we'll get our answer. So FAB is equivalent to 10 kilograms multiplied by 2.3. That's some simple math, and it comes out to 23 newtons. There we go.